This is Unit 7, Lesson 8, an exponential application and its graph, compound interest. And boy, I hope you're ready for an exciting lesson. I took an entire college class on soils. My final project was on blowing sand, and it was more interesting than this is going to be. Exponential functions are used to model bacteria growth, decay, the amount of drug decrease, population increase or decrease, compound interest growth, and the depreciation value of an item. Yeehaw. An exponential function is written as the f of x is equal to a times b, and b is to the power of x, where a is the initial value and b is the multiplier. Wow, I'm bored already. All right, suppose Aisha invests $5,000 in an account that earns 4% interest compounded annually. Find the value of Aisha's account each year for 20 years. Okay, first of all, Aisha's rich because I don't have $5,000. Second of all, I should understand what 4% interest compounded annually means because I'm an adult, but I don't care because in 20 years I will probably be dead. So the first thing we're going to make is a graph to model the value of Aisha's account each year. This means that the account increases by 4% each year. That means that the annual growth factor is 104% because it has the 100% from what was in there initially. This is in there. The bank's not going to take your money. And you get 4% from the bank. The bank is going to give you money every year for putting money into the bank. Okay? This is what our formula is going to look like. It's V of N is equal to $5,000. That's your initial deposit times 1.04. 1 is your initial investment, which is 100%. 0.04 is 4%, which is the compound interest that the bank is going to give you, to the power of n. And n is going to be the number of years, which is the variable that's going to change. Okay, to figure out the domain and range for this, we know that we need to figure out all the possible x values and the possible y values. So we only need to worry about Aisha's account over a 20-year period. So a reasonable domain for n is going to be n is greater than or equal to 0, so it starts at 0, and n is less than or equal to 20, so it stops at 20. We only need our graph to go from 0 to 20, okay? Let's see. At the year 0, the value of Aisha's account is $5,000 because that's her initial deposit. So our first point is going to be 0 and 5,000. Okay. In 20 years, the value of her account will be approximately $10,956 because it's got that 0.104. It's going to be a messy number. Okay. So the range for the y-axis is going to be V is greater than or equal to 0 because we are starting at $0, sorry, and V is less than or equal to 11,000 because our top range is going to be about 10,956. So now that we know a reasonable range for our x and y axes, we can start graphing this. So your graph is going to look roughly like this. I know my graphs are messy. I apologize. I'm not going to take the time to go and actually do them neatly when there's this many. So years are going to go on the bottom. They chose to go by 2 years. Every 2 years, 2, 4, 6, 8, 10. And then value is up here, and they started at 500 and then went 1,500, 2,500, 3,500, all the way up to 11,500. So this is roughly what your graph is going to look like. I'm doing good. So when Ileana is born, her parents invest $10,000 in an account paying 5% interest compounded annually for her college fund. Ileana's parents are rich. Let n represent the number of years the money is in the account. What is a reasonable domain? So we know that for n to be the number of years, okay, then n is going to start at 0, so n is greater than or equal to 0. And most people go to college right after high school, so n is going to stop at 18. That's a reasonable domain because it's when she's going to be born until when she will reasonably go to college. The dogs are playing, so it's going to get loud. Sorry. Suppose Mr. Juarez purchased a new car for $25,000. The car will lose 10% of its value each year. If this is a new car, it's a really strange car. It might be like a wagon, not a car, because cars don't cost $25,000. So we're going to make a graph to model the depreciation of the car's value. Depreciation is a decrease in the value of an item over time. The more you drive a car, the less it's worth. Okay? So the car loses 10% in value each year. That means it will still retain 90% of its value. Okay? Our formula is going to look like V of n is equal to $25,000, the original purchase price, times 0.90, which is 90% to the value of n, with n representing the number of years, and V is the value of the car. So now we need to determine a reasonable domain and range. Okay, so this is telling us, I wouldn't know this because I drive my cars like forever, but on average people keep a car purchased as new for around 8 years. So we're going to go further than that for our domain, since people like me will keep the car for a longer. So they're saying the reasonable domain is from 0 years to 15 years. In math notation, that's how you'd write it. N is greater than or equal to 0 and less than or equal to 15. If you plug 15 into this formula, you'll find out that in 15 years, the car is going to be worth $5,147. So the axis, the money axis, which is going to be Y, the vertical axis, is going to go from 0, because that, at 20, it's going to start at 0, but your first mark will be at 25,000 because it's going to go down, and it will go down to 5,147. So it needs to start at 0 and go all the way up to 25,000 on the y-axis. On the x-axis, which is years, it's going to go from 0 to 15. Keep in mind that the car is never going to be worth $0. Even if your car doesn't drive anymore and it was in a horrific accident, it's still worth money for the scrap metal. So it's never going to touch the x-axis. Exponential graphs never touch the x-axis. They never go all the way to 0. This is roughly what your graph should look like. For the years, we're going by every 1 year, so 1, 2, 3, 4, 5. And by the value of the car, we're going by every $1,000. Mateo drinks a cup of coffee with 140 milligrams of caffeine. Each hour, the caffeine decreases by 10% in his body. This situation is modeled by the function C of h is equal to 140 times 0.9 to the power of h, where h is the number of hours since drinking the coffee, and C is the number of milligrams of caffeine remaining in Mateo's body. What is the range? So the range is going to be C, and it's going to go from 0 to 140. The range represents the possible values for the dependent variable, and that's the amount of caffeine in Mateo's body. Written as an inequality, it's C is greater than 0, but it's less than or equal to 140, because remember, it's never going to touch the x-axis because it's an exponential function. The dogs are playing again. Research scientists are trying to predict tumor growth in order to better treat patients. One experiment started with a 1 millimeter tumor in the lab. They found that without intervention or treatment, the tumor will double in size every 2 months. They want us to make a graph to model the size of the tumor over 2 years. Wow, the dogs are really loud. So the formula is going to look like the S of n is equal to 1 times 2 to the power of n, where n is the number of 2-month periods and S is the size of the tumor in millimeters. And we want to know what a reasonable domain and range is. A 2-year period contains 12 2-month periods. So a reasonable domain is from 0 to 12. That would be written as n is greater than or equal to 0 and n is less than or equal to 12. Now, if we take 12 and plug it into this formula, we'll find out that in 2 years, the size of the tumor will be 4,096 millimeters. So the range, a reasonable range for S, is going to be 0 to 4,200. You're going to go 4,200 instead of 4,100 because we're counting by units of 200. That's written as S is greater than 0 but less than 4,200. For the number of 2-month periods, you're going to count by ones. And for the number of the size of the tumor, you're going to count by 200s. If you count by 100s on this axis, you're going to have 41 intervals, and that's going to be a really big graph. Your graph will look something like that. Okay, Dr. O'Hare performs a science experiment. There are 100,000 bacteria present in a petri dish. Dr. O'Hare adds an antibiotic. She observes that every hour the number of bacteria is reduced by half. Make a graph to model the number of bacteria present each hour. The exponential function that models this situation is b of h is equal to 100,000 times 1/2 to the power of h, where h is the number of hours and b is the number of bacteria. Determine a reasonable domain and range. Go ahead and pause this video and then come back with your answer. Some guess and check is needed here. So they chose to do h as a value of 10, and when they plugged it into the formula and solved it, they got 98. So then they did 12 and they got 24. So it's going down really quickly. So they did 14 and they got 6. So in 14 hours, there's only going to be 6 bacteria present in the petri dish. Technically, the bacteria will never reach 0. So going up to 15 hours is close enough. So a reasonable domain is going to be h is greater than or equal to 0 and less than or equal to 15. The range is a lot easier to figure out, and we know it should be between 0 and 100,000 because there's 100,000 bacteria at the start, so there's never going to be more than that. So for the hours, we're going to count by 1 every hour. The number is going to change. And then for the scale for the bacteria, we're going to count by 5,000 because it drops so quickly. When you're dealing with a problem like this that has such a huge range that it drops, when you're zoomed out and showing the whole gambit of it, it looks like when you hit about 8 that it just bottoms out. But when you zoom in, you can see better detail that it doesn't. When you zoom in, you can see that it doesn't actually bottom out until you hit 15. Honestly, for this entire lesson, I wouldn't bother even trying to graph this stuff. I would just use a graphing calculator. The program that Angie is using actually has a graphing calculator built into the program, so I don't consider it cheating or anything else. It's just you're dealing with such huge numbers, and when you get to the point that they're telling you you have to zoom in, you can't zoom in on a graph that you made by hand. Anya is studying the growth of a beetle population. She observes that the beetle population doubles every month. Anya begins the project with 6 beetles. The situation is modeled by the function b of n equals 6 times 2 to the power of n, where n is the number of months and b is the number of beetles. If you want to find the beetle population in 1 year, what is a reasonable domain and range and the scale of each? Pause the video, figure it out. Okay, so the domain would be n is greater than or equal to 0 and less than or equal to 12. And the scale would be 1. And the domain is your x value. Your range is going to be b is greater than 0 or less than or equal to 25,000. And your scale is going to be 1,000. And we get this 25,000 by figuring out using this formula and plugging in 12 for the value of n. And when you solve it, you find out that your top value is going to be 25,000. 12 months in a year, so that's where we got the 12. And 25,000 is because the answer, when you plug 12 into this equation, is 24,576 beetles. So you'll need 25,000 in order to have that total included in your graph. Half of a radioactive isotope remains after every 4 hours that passes. Suppose 50 milligrams of the isotope is created in an experiment. This situation is modeled by the function I of n is equal to 50 times 0.5 to the power of n, where n is the number of 4-hour periods and I is the number of milligrams of the isotope remaining. If the isotope is observed for 36 hours, what is a reasonable domain and range for this situation and the scale of each? So 36 hours total. And then it wants you to make a graph and model the depreciation of the radioactive isotope's number of milligrams. Again, I would use a graphing calculator to make the graph, so find a reasonable domain and range and a scale. Pause it and come back. So the domain would be n is greater than, n is greater than or equal to 0 and less than or equal to 9 with a scale of 1, but each 1 is a 4-hour period. So even though it goes up to 9, it's actually going up to 36 hours. The range would be I is greater than 0 or less than or equal to 50 with a scale of 5. We get that 50 from right here in the problem. It tells us how far up it's going to go. The independent variable is n. Let's see, the dependent variable is the number of milligrams of the isotope remaining, or I. And then the graph is going to be kind of a Scoopy looking thing like this again, but again, just use a graphing calculator. There's no benefit to you actually graphing this yourself. This is question 1 on your practice. It says Karen purchased a car for $40,000 by taking out a loan that will take 7 years to pay off. Given the car depreciates in value by 11% each year, the situation can be modeled by the equation V of t equals 40,000 times 0.89 to the power of t, where V is the value of the car after t years. If Karen wants to know how much the car will be worth in 7 years, which of the following options would be an appropriate range? And then it gives you a selection of ranges. Pause the video, try to figure out, come back. Okay, so we know that the domain is the x-axis, and we know that the range is the y-axis. So for this one, the domain is going to be the time. So we already know that they want us to tell them the range for this problem. So time is going to be out. Time is 7 years, so we already know this one and this one are not the correct answer. It has to be one of these. And the only difference between these, we have 0 at the beginning and 40,000 at the end. The only difference is, do we have t or v in here? It tells us v is the value of the car after t years. So t is time, v is value. The range is our value. It's not going to be time, so it has to be number 2 because it's dealing with value. Question 1 on the quick check gives you a word problem and wants you to do the exact same thing. Okay, because I'm bored, I found something random on my computer desk. I think it's from McDonald's. I think it's an Adopt Me pet. It's got something on it. It looks like ink or something. It's a little shark and he goes rawr. When you need to graph an exponential function, other than just sketching it, making a table of values using technology or calculate the values using an equation. So for this problem, y is equal to 4 times 3 to the power of x. They're giving us the values of x is equal to 0 and x is equal to 4, and it wants us to create a table. And the table they're giving us has values between 0 and 4, so I guess we're going to do 0, 1, 2, 3, and 4. I don't know why, but we are. So this is what your table's going to look like. We've done this a lot. Just take your value for x, plug it into this equation, and solve for y. So here's all of the problems worked out. Go ahead and pause it if you need to go over the math. But here's our table filled out as well. So now we have our x, y coordinates, which we can use to graph. And I was hoping that they would give us something that was easy to graph, but they didn't, because look, we have 0, 1, 2, 3, 4, and then we have 4 all the way up to 324. So again, I am an evil, lazy person, and I would use a graphing calculator because it's just going to be easier. Now we have the function f of x is equal to 100 times 0.5 to the power of x, and it gives us this table, which I didn't draw a line right there, let's fix that, of x and the f of x, and it wants us to complete the table. So you don't need to worry about 0, 1, 4, or 5, they're completed. You just need to plug in the values for x of 2 and 3 and solve. Pause it, do it. Here you go, your math. Your answers are 25 and 12.5. Pause it if you need to go over the numbers. Dr. Yamamoto is studying the growth of bacteria in a lab experiment. He puts 50 bacteria in a petri dish to start and observes that the population doubles in size every hour. This situation is modeled by the function b of h is equal to 50 times 2 to the power of h, where h represents the number of hours and b represents the number of bacteria. This is a model of exponential growth. Create the graph of this function by plotting points. Show the growth of the bacteria for the first 5 hours. So first make a table of values and they say using technology, or calculate the values using the equation. So if you have a calculator that's fancy enough to do this, go ahead and use it. I don't know how to do that because I'm a child of the 80s. So go ahead and use math if you need to. They use the points 0 through 5 for x. And then I would also use technology to graph it, because why make it harder than it has to be? By this point, you should be able to do x, y points on a graph. Pause it, do it. This is what your table is going to look like. I did one problem as an example where I used 2 as the value of h. Go ahead, look it over if you need to, pause it. I'm not even going to bother drawing the graphs anymore because mine are not super precise, and you can use a calculator to do it. The next problem says, suppose a patient is given a 400 milligram dose of amoxicillin. The concentration of the drug in the patient's bloodstream is 70% from 1 hour to the next. The amoxicillin metabolizes at 30% each hour. When a substance metabolizes, it is affected by chemical processes in the body so that it is broken down, absorbed, and used. This situation is modeled by the function m of h is equal to 400 times 0.70 to the power of h, where h represents the number of hours and m represents the number of milligrams of amoxicillin. This is a model of exponential decay, and it wants you to create a graph and show the decay for the medicine for 8 hours after taking the dose. So the table is going to have the values of h from 0 to 8. I started filling it out and realized I hadn't recorded the problem yet. So go ahead and figure out the rest of the values, and then you can create a graph using your wonderful little graphing calculator. There's the rest of the table and an example showing h is a value of 6. They want you to round it to the nearest whole number. So that is what I did. All right, let's look at this problem. Find the missing values in the table for the function f of x is equal to 1000 times 1.05 to the power of x. Round answers to the nearest whole. So this already gives us the answers for 1, 3, and 5 for the value of x. We need to find 0, 2, and 4. Go ahead and pause the video and do that, and then come back. And there are your answers and all of the math. Pause the video if you need to. By the way, I had to Google to remember that when you take something to an exponent of 0, then the answer is 1. I had to do that earlier in the lesson, but yeah, because I'm smart. Suppose the population of a small town is growing by 10% annually. The town's population in 2022 is 500 people. That's a really small town. This situation is modeled by the function p of n is equal to 500 times 1.10 to the power of n, where n represents the number of years since 2022 and p represents the population. This is a model of exponential growth. Woo! Create the graph of this function by plotting points. Show the growth of this town's population through 2027. This one is actually not a nightmare of a graph to make, so go ahead and actually try on this one. So make a table of values and round the numbers to the nearest whole because P of n represents people and you can't have a partial person unless you want to commit a felony and end up in prison for the rest of your life. Use the values of n 0 through 5. Pause it and go do it. Okay, there's our table with the values and an example of solving for n to the value of 1. Pause it if you need to. And there's roughly what your graph should look like. See, it wasn't as nightmarish as most of them have been. Okay, so this one is a word problem about Miss O'Connor, who invested $4,000 into an account earning 4% interest compounded annually. Complete the table to show how much money she has in her account for the last 5 years using the function d of y is equal to 4,000 times 1.04 to the power of y, where d represents the money in her account and y represents the number of years. Round answers to the nearest dollar. I feel like this is beating a dead horse at this point because this is stuff we've been doing over and 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 over. So I'm just going to fill out the table and call it good. If you feel like you need to, go ahead and pause it and solve this on your own and then come back and get the answers. And there's your answers for you if you want to double check them. We've got another one coming up that says John purchased a $1,500 laptop. The laptop depreciates by 25% in value each year. Complete the table to show the value of the laptop for the first 5 years using the function v of t is equal to 1,500 times 0.75 to the value of t, where v represents the value of the laptop and t represents time in years. Round answer to the nearest dollar. Okay, so here's what the problem looks like. Go ahead and pause it and solve it. If you feel like it will be beneficial, come back for the answers. And there's your answers for you. Yay! I swear this lesson will end eventually. Okay, this is your practice question number 2. It says this table presents values of x and f and x with one missing entry to be determined, which is 4. And it says find the missing value in the table for the exponential function f of x is equal to 3 times 1.2 to the power of x. Round your answer to 2 decimal places. Go ahead and pause it, try to solve it, come back. So plugging the value of 4 in for x, we have 3 times 1.2 to the value of, to the exponent of 4. So 1.2 to the 4th power is 2.0736. We just drop the 3 down, multiply these two, and you get 6.2208. It says to round your answer to 2 decimal places, so your answer is 6.22. This is question 3 on your practice. It says this table tracks the anesthetic amount, 320 milligrams over time, as it metabolizes at a rate of 25% per hour, modeled by an exponential equation. Kaysen is scheduled to get his wisdom teeth removed. The oral surgeon gives him a local anesthetic to numb his mouth. Before surgery, Kaysen is given 320 milligrams of the anesthetic, which metabolizes at a rate of 25% per hour. The situation can be modeled using the exponential equation f of x is equal to 320 times 0.75 to the power of x. Finish the chart to determine which graph displays the correct plotted points for the situation. And then there's several graphs to choose from. So go ahead and pause it, finish filling out this table, and then we'll figure out which graph is correct. Okay, here's all the math and the completed table. Go ahead and pause this if you need to, and we'll go and look at the different charts and see which one's correct. So here's our first one. Our first point should be 0 and 320. That's pretty reasonable. Next should be 1 and 240. Okay, I could do that. 3 and 135. Okay. 4 and 101. Okay. And 5 and 76. Yeah, this is probably it. Let's double check. So we should have 0 and 320. We know that's... So 320 is not the hours, so we know this one is wrong because we're not dealing with 320 hours. So 0 and 320, that's possible. 1 and 240. 1 and 240, no way. It's clear down here, so that one's not right. That's it. Those are our only options, so it has to be that first one. I'll go back and show you again because sometimes they mess with the order. You can't just say, oh, it's number 1, because on Mom Bawb's paper it was number 1. It's this one that looks like this. So it has, for milligrams, it has 0 to 350. For hours, it has 0 to 7, and it's got a swoop like that. Question number 2 on your quick check is the same scenario as is number 3. Number 2 doesn't require you to complete the table, though you probably have to figure out which graph is right. Number 3 is set up exactly the same. Time for something fun off my desk. This is a little bird that Dad Bob brought me from Alaska that somebody carved out of bone, which I think is, gross, but he thinks is awesome. And it has this little nest with little eggs in it. Okay, yeah, isn't that awesome? Last section. So you may have noticed that these graphs that we're looking at, these exponential functions, tend to have a curve in them. They're usually not a straight line like the linear functions. And that's because whether it's increasing or decreasing, it doesn't do it at a steady rate the way a line does. It might decrease quickly and then slowly, or it might go slowly and then quickly. It might increase slowly and then quickly. It's just how exponential functions work, okay? So we're working on interpreting graphs now and figuring out what they mean. So this is a graph that we used earlier that I drew really sloppily, but this is a better representation. So notice these key features. First of all, as h increases, b of h increases. So as this goes up, this goes up. First, it increases really slowly. It has this really gradual increase that's almost horizontal. And then it starts increasing really rapidly. It's almost level at first, then it has a steep increase. Okay. Sometimes the domain needs to be increased for the steep increase to be visible. So look at these changes. So first, from here to here, from 0 to 1, we only have an increase of 50. From the next step, we have an increase of 100. The next step is an increase of 200, then 400, then 800. That's an exponential increase. You can see it on this y-axis. First it's 50, then it's 100, then it's 200, then it's 400. Okay, it's increasing based on a power that it's raised to. The increases are getting larger and larger. That's why the graph is steeper. All right. So remember, a graph has different quadrants. The quadrants are numbered opposite of the way you would go around a compass. So normally on a compass we'd go north, east, west, northeast, southwest. I'm so good. I'm so good. But this is going opposite. This is going counterclockwise. So it's 1, 2, 3, 4. These, both values are positive. Then we have negative x, positive y. Both are negative. And then we have positive x, negative y. So the example that we just looked at, which I've moved, oh, it's right there. Okay. This is all in quadrant 1, where it's positive, positive. Okay. We've seen a lot of those lately, where we're dealing with only positive values. So if we're going to interpret this graph and the way this line changes, this curve changes, we would say that as x increases, y increases slowly at first and then quickly. Let's look at the key features of this graph. As h increases, m of h decreases. So as this gets bigger, this gets smaller. From left to right, the graph has a steep decline at first. It goes down really quickly at first, and then it almost levels off. So it's fast at first and then slow. Really fast descent, and then it gets slow. Kind of like a slide in a playground. Not all decreases look like this. Sometimes it might be really slow at first and then go really fast. This is just an example. So if you look, the first initial decrease is 120, then it goes to 84, then 59, then 41, then 29, then 20, then 14. So you can see when you look at the differences between these, that the amount of decrease is getting smaller and smaller each time. And then the last one is 10. The decreases are getting smaller and smaller. That's why the graph starts off with a steep decline and then almost levels off. Okay, all of that is important. So this one shows an increase. This one shows a decrease. So how would you explain this? What would you say to explain this? As x increases, y decreases, and is it quickly or slowly at first? It decreases quickly at first, and then it decreases slowly. 30 Cool Beans cafes opened in Grand City in 2010. Since then, the number of the cafes in the city has been growing at an annual rate of 25%. This situation is modeled by the function c of n is equal to 30 times 1.25 to the power of n, where n represents the number of years since 2010 and c represents the number of cafes. So I'm going to read you 4 statements, and I want you to tell me if it's true or not true. So the first one, as n increases, c increases slowly at first and then quickly. Is that true or not true? Well, we know it's going to increase because we're keeping all of the stores that we had at the beginning, and we're adding more each year. So it's going to start increasing, and it's going to do it slowly at first because it's increasing by 25%. So if you have one store, then the next year you'll have 1.25. The year after that, you'll have 1.5, right? So it's going to increase slowly at first, and then it's going to go quickly. So that is a true statement. The next statement is the C values include 0 cafes. So in this problem, do we have 0 cafes? That's false because we're starting with 30. There's no point where the line is going to be at 0 for the number of cafes. The next statement is the y-intercept is greater than 0. So on our graph, where it's going to cross the y-line is greater than 0. True or false? True, because we're starting with 30 cafes. We are not starting with 0 cafes. The last statement is the n values include all real numbers. So n is the number of years. Does that include all real numbers? That is false because we are only looking at the years from 2010 on. Angie just came out and she's like, you're still working on that? These are only 30-minute videos. I've been working on this for 2.5 hours and I'm still not done. Yeah, that's how long it takes to do all this junk. Okay, so this problem says radioactive iodine I-131 therapy is a nuclear medicine treatment. Doctors use it to treat an overactive thyroid, a condition called hyperthyroidism. My brother has that. I have hypothyroidism. Suppose a dose of 240 mbq megabecquerels is given to a patient. Half of the drug remains every 8 days. This situation is modeled by the equation d of n equals 240 times 0.5 to the power of n, where n represents the number of 8-day periods and d represents the number of mbq. Name 2 key features of the exponential graph for this situation. My brother had this done. He had his thyroid irradiated and it killed it because it was kicking out too much thyroid hormone all the time, and so his thyroid was killing him. So they had to kill his thyroid. Hey, something interesting happened in this lesson. All right, so 2 key features of this exponential graph for this situation. Pause it, come up with 2, come back. Okay, some example answers are, as n increases, n is, I don't know if they told us, the number of 8-day periods. So as more time passes, d decreases quickly at first and then slowly. So the amount of radioactive iodine that's in their system or in my brother's system decreases quickly at first and then it slows down. And the reason we know that is because we're dealing with 0.5. We're dealing with a fraction here. So at first it's going to get cut in half, and when anything gets cut in half, a lot of it's gone. I always use pizza as an example. So if half the pizza's gone, you're going to go, oh. But then when you so a pizza normally has 8 pieces. So 4 pieces are gone and you're like, oh. And the next day 2 pieces are gone and you're like, oh. And then the next day 1 piece is gone and you're like, And then the next day half of a piece is gone and you're like, oh well. And then the next day a quarter of a piece is gone and you're like, I care why. So it decreases fast at first and then it levels out. Okay, that's one thing you could say about the graph. The y-intercept is greater than 0 because we're starting at 240. We're not starting at 0. They're using 240 MBQ of radiation. We're starting there and then it's going down. The n values, which are the 8-day periods, are greater than 0 or equal to until the drug has run its course. So my brother had his thyroid irradiated, 30 years ago probably. So he has no radiation left in his body. It's gone by now, guaranteed. Or it's some infinitesimally small amount that doesn't matter anymore. The d values are greater than 0 because the graph will never touch the x-axis. So according to this, he will always have a little tiny bit of radiation left in him because it just keeps dividing by itself over and over and over and over. But it doesn't really matter because it's such a small amount, it's not ever going to hurt him. So now we have this graph that we're looking at. It says the population of a small town is about 4,000 and is growing at a rate of 8% annually. This situation can be modeled by the exponential equation P of t is equal to 4,000 times 1.08 to the power of t, where P is the population and t is the time in years. The town council made a graph to represent the predicted population growth of the town. Identify the domain and range of the graph along with 2 other key features. Round any decimals to the nearest whole number. There's your formula, and so go ahead and pause this, figure out the domain, the range, and then come up with 2 key features for the graph. Okay, the domain is our time, and it means that time is greater than 0, greater than or equal to 0, because it starts at 0. Our range is the population, and it starts at 4,000, so population is greater than or equal to 4,000. And you can see this line just comes up at a nice, it is curved just slightly if you look, but mostly it's just a steady increase because this is so close to just 1. This is so close. So some points you could make about this is it says as t increases, p increases slowly at first and then more quickly. This is really hard to see on this graph. This is one of those things that you would have to use a graphing calculator and zoom in to be able to see this better. But you can say that from looking here because it's 0.08. We know this is going to increase because it's above 1, but it's going to do it slowly because it's clear down here at 0.08. So it's slowly and then more quickly. We can also say the y-intercept is 4,000. So the p-values will always be greater than 4,000. And we can definitely say that this line is never going to touch the x-axis. That's it for this lesson. We survived. This is definitely the longest video by far, and most of it really wasn't hard. So I don't understand what they're doing with the lessons. Okay, bye.